and we are looking particularly at velocity fields, acceleration fields. In class on Tuesday, we're going to start talking about conservation laws, conservation of energy, conservation of mass, and we'll do that with something called the Reynolds transport theorem. For now, we'll work through some problems here that basically test our calculus skills. A little bit of background, though, real quick. You may have heard a little bit about Euler and Lagrange, or Eulerian and Lagrangian approaches to fluid mechanics. And they're slightly different. Euler was, you can see, a little bit older than Lagrange. He was a well-known mathematician. In Europe, there are a number of stamps with his likeness on them, so that's what you see on the left. Lagrange actually grew up and became a mathematician as well. He studied Euler's approach to mathematics and decided he had a different approach, a different idea. He's perhaps not as well known, and so he only has one stamp with his likeness on it. But Lagrange really did upset the mathematical world by sort of taking a different view of the world. And so we'll talk about that here for just a moment. Lagrange's approach is essentially to track the motion of individual particles. So let's just say we took a cannon here with a cannonball coming out of it. You can imagine at different times this might be sort of a basic physics sort of approach to the world, but we could think about that cannonball. If we were moving along with it, where would it be at different times? What would its position vector be? What would its velocity, its acceleration be? So we could think about just the ball itself moving through as a projectile through the air. So position and velocity are essentially functions of time and the initial conditions. So we think about like an acceleration, a position, etc., coming out from that cannon, and then from there everything is a function of time, right? After it started its motion. That's different than Euler's approach. Another way of thinking about Lagrange approaches to the world, this is a map on the right hand side of a bay, Glacier Bay, Alaska, where a colleague of mine, Dave Hill, had put out this sort of floating data collector. So it was getting temperature and salinity and so forth from the water, and he just let it float around the bay. So it moved around in all these different colors on sort of the path of this floating data collector through time. So we can track oceanographic sort of drifter buoys, for example, and we could think about the velocity and acceleration being the first and second derivatives of the position vector as this thing moves around the world, right? That is all different than Euler's approach, which was to say, it's really hard. And actually, it was Lagrange's evolution on Euler's view of the world that gave us this particle tracking idea. But prior to that, then Euler's approach was to say, it's kind of hard to track fluid particles. Why don't we just take a view of the world? I'm going to take a view and I'm going to look at what changes in front of me. So the approach focuses on dynamics within a fixed volume or in space. And we don't necessarily care about the history of or the velocity of a particle, for example. So we are looking at the world. Something comes into that view. We track how things are changing in that view that we have, and then we track what happens as things go. So within this volume, flow or field variables are defined everywhere, right? So we know exactly what's going on in our field, and we think about things coming in and things going out. And the difference then on the left-hand side, an Eulerian view of the world might be on a fixed pier. We have some instrument that is measuring, say, velocities of water moving by. On the right-hand side, the Lagrangian view of the world is we put a buoy out in the world and watch it move around based on how the flows change its position through time and space. Okay, so as you see Eulerian and Lagrangian sort of perceptions or invocations in the textbook, I just wanted you to make sure you had that perspective. All right, Let's move on. Okay, so the first problem here is problem 4.2, practice problem 4.2 from the back of your Wiley Plus chapter. And the problem statement here is that the surface velocity of a river is measured at several locations x and can be reasonably represented by v is equal to v naught plus delta v times 1 minus e to the minus a times x, where v naught, delta v, and a are all constants, and the Lagrangian description of the velocity of a fluid particle flowing along the surface, we're to find the Lagrangian description of the velocity of a fluid particle flowing at the surface if x is equal to 0 and time is equal to 0. Okay, so we're going with sort of these initial locations. All right, so let me get my pen going here. Okay, so essentially we have velocity, or we could say dx dt, right, as a velocity representation, is equal to v, is equal to this v naught plus delta v times 1 minus e to the minus ax, right? So that's just a rewriting of that. Eventually, what we're going to do on the next slide then is integrate both sides. Well, we're going to move delta t or dt over, so dx dt will separate here and then integrate. So let's take a look at that. If we rewrite this, we can say that we have dx over v naught plus delta v minus delta v e to the minus ax. So I've expanded that out. And then this is equal to dt, and we can integrate both sides here from 0 to some x value, and over here on the right hand side from 0 to some t value, right? We could take this one step further and provide sort of what this evaluation looks like. And so if we do work out these integrals, we would get x over v naught plus delta v minus 1 over v naught plus, that should have been a delta v, times minus a times the natural log of v naught plus delta v minus delta v e to the minus ax. And that would be evaluated from 0 to x. And on the right-hand side, we just say is equal to t, right? If we integrate dt from 0 to t, we just get t. So if we substitute the limits that we're given, so recall we said that initial condition, so x equals 0, t equals 0, and we know that v is equal to some v naught, some starting velocity. If we substitute those in, we basically end up with x over v naught plus delta v plus 1 over a times v naught plus delta v times the natural log of, now we have v naught plus delta v minus delta v e to the minus ax over v naught is equal to t. Let's see, I'm just realizing up here I missed a bracket or a parenthesis, but anyway, that goes in there. Okay, so then we could rearrange this and try to simplify a little bit. So we end up with x plus 1 over a times the natural log of 1 plus delta v times 1, oops, this should be a v, delta v, 1 minus e to the minus ax. All of this over v naught, so the 1 plus stays out. So there's that is equal to v naught plus delta v times t. Okay, so we factored out a V naught plus delta V from the left-hand side, multiplied through by that, so that ends up on the right-hand side. And then using the original equation for V, we basically get V minus V naught over delta V is equal to 1 minus E to the minus AX. And we can rearrange that as E to the minus AX is equal to 1 minus V naught over delta V. Okay, so we need to take this one step further, which is to put this in terms of X. I'll do that on the next slide. Okay, just let you guys catch up there for a sec if you're writing this out. Okay, so now we end up with X being equal to minus 1 over A times the natural log of 1 minus V naught over delta V. Okay, and then we're going to substitute in these expressions for E to the minus AX and X into equation 1, which was essentially this one right here. So this is equation 1. All right, so now let's put this and X into that equation. So when we substitute these in, we're going to end up with minus 1 over A times the natural log of 1 minus V naught over delta V plus 1 over A times the natural log of delta V plus V minus V naught over V naught, which is equal to V naught plus delta V times T. And then we can simplify this a little bit. So we get 1 over A times the natural log of V over V naught times delta V over delta V minus V plus V naught. And we'll close that is equal to V naught plus delta V times T on the outside of that. And then we end up with V over V naught times delta V over delta V. That should be a minus V plus V naught is equal to E to the A times V naught plus delta V times T. And we can take it a step further then. V times delta V, if we simplify this on the left-hand side, so V times delta V is equal to V naught times V naught plus delta V minus V times E to the A V naught times V naught plus delta V, and then all of that times T. And then this gets a little bit messier here. We end up with V times delta V plus V naught E to the A V naught plus delta V times T. And then that is all equal to V naught times V naught plus delta V times E to the A V naught times V naught plus V. Sorry, that should be a delta V. And then times T on the outside of that. And all of this boils down to V is equal to V naught times V naught plus delta V over V naught plus delta V naught e to the minus a times V naught plus delta V and then times t. So that is our entire summary, which is complicated, of course, but we do see that we end up with some velocity at any time is equal to a function of our initial velocity times the change in v and as a function of time. Okay, so that's the Lagrangian view of the world. All we did was take some simple derivatives and integrals, but of course the calculus got a little bit complicated there. Okay, let's go on to the next problem. And here we're going to use calculus again, but we're going to look at acceleration instead of just velocity or position. So the velocity components of u and v of a two-dimensional flow are given by u is equal to ax plus bx over x squared times y squared, and v is equal to ay plus by over x squared times y squared. So a and b are constants. The question here, or what we're supposed to find, is calculate the acceleration. Okay, so we have these two givens. We are looking essentially for acceleration in the x direction and acceleration in the y direction. Okay, those two things. So ax, we noted kind of dryly perhaps last week, is equal to u del x plus v del y, and ay, the acceleration in the y direction, is equal to u del v del x plus v del y. Okay, so what we're going to end up doing then is taking the derivative of the u and v components that were given with respect to x, with respect to y, plug them into these equations. All right. So if we substitute into, let's work on ax first. So if we work on this ax component, we'll save ay for the next slide. Let's see, we will have ax is equal to a times x plus b over xy squared times del x of ax, a times x plus b over xy squared, and then we're going to add a times y plus b over x squared y, and then multiply by del y of this expression, which is a times x plus b over xy squared. Okay. Now we can simplify this. Let's take the derivatives there. So we have the partial with respect to x of the second term and the partial with respect to y of that last term on the end. So when we do that, we end up with ax, oh, that's supposed to be an ax, a times x, plus b over xy squared, right? That didn't change. That's supposed to be a parenthesis. And then we multiply now by a minus b over x squared y squared, right? So when we take the derivative of this term with respect to x, we get a minus b over x squared y squared. And then we're going to add, now we'll have a times y plus b over x squared y, so that part doesn't change. And now when we take the derivative of this with respect to y, we end up with minus 2b, that's supposed to be a b, not a 6, 2 times b over x times y cubed. Okay. All right, so we can simplify this now by gathering some of these like terms together and so forth, and working through this. So let's do that on the next slide. We end up with, to simplify this a little bit, this is equal to a squared x plus a times b over xy squared minus a times b over xy squared. So you can see things are going to simplify a little bit more. Minus b squared over x cubed y to the fourth power, and then minus 2 times a times b over xy squared. I need to move this somewhere else. Just get it out of my way here. Do that for now. And then minus 2 times b squared over x cubed y to the fourth. Okay, so this simplifies a little bit to be equal to a squared x minus 2ab over x times y squared. And then minus 3b squared over x cubed y to the fourth, which basically comes out to be equal to x times, oops, that's supposed to be a parenthesis, a squared times minus 2ab over x squared y squared, and then minus 3b squared over x to the fourth y to the fourth. Okay, and what we end up with then is ax is equal to x times a minus 3b, so a is our acceleration, 3b x squared y squared squared, close parenthesis, open the next one, a plus b over x squared y squared. Okay, so there is the acceleration in our x direction that basically just came out of taking those partial differentials in the x and y direction. Now, we're going to do the same thing real quick for the y direction. So the acceleration in the y direction is equal to, in this case, a times x plus b over xy squared, close parenthesis. Now we have the partial del x of a times y plus b over x squared y, close parenthesis, plus, then we have a times y plus b over x squared y, and now we multiply by the partial in the with respect to y of ay plus b over x squared y. Okay. Now, again, we're going to take those two derivatives there, those two partials, one with respect to y, one with respect to x, and then we'll get a times x plus b over x y squared. Again, no change there, but now we have minus 2b over x cubed times y, and then we add a times y plus b over x squared y, and then we multiply by a minus b over x squared y squared. Okay. Now, again, we can simplify this a little bit. So we're going to do this by saying minus 2 times AB over x squared y minus 2b squared over x to the fourth, y to the third, plus a squared y plus a times b over, that's a times b, over x squared times y minus a times b, oops, let me close that, minus a times b over x squared y. So you can see those are going to cancel, and then we subtract b squared over x to the fourth, y to the third. And then we take this another step and we say a squared y minus times y minus 2 times a times b over x squared times y minus 3b squared over x to the fourth, y to the third is equal to then y times a squared minus 2 times a times b over x squared y squared minus 3b squared over x to the fourth, y to the fourth. Okay, and all of this comes down to ay being equal to y times a minus 3b over x squared y squared times a plus b over x squared y squared. Oops, that should be a parenthesis. Okay, so there we go. We've got ax, the x component of acceleration, and the y component of acceleration, again, through a fair bit of calculus. Okay? All right, let's move on to problem number 3 that we have set up here. Acceleration along a flow line. So as a valve is opened, water flows through the diffuser, as shown in the figure below, at an increasing flow rate so that the velocity along the center line is given by v is equal to u multiplied by the I unit vector, which is equal to v naught times 1 minus e to the minus ct times 1 minus x over L times the unit vector I, or I hat, where u naught, c, and L are constants. The question here, or the objective, is to determine the acceleration as a function of both x and t. If v naught is equal to 10 feet per second and L is equal to 5 feet, what value of c, other than c equals 0, is needed to make the acceleration 0 for any x at t equals 1 second? Explain how the acceleration can be 0 if the flow rate is increasing with time. Okay, before we get going, let's just take a look at the system. We have water coming in from the left. It's going through what we call a diffuser. The diffuser, of course, is increasing the cross-sectional area with time. So from a gut check, before we do any math, we would typically expect that if the flow rate is staying constant, right, and we had water flowing through this, then the velocity is going to drop through time, right, because A is increasing. So if Q at the left-hand side has to equal Q at the right-hand side, and A keeps getting bigger and bigger and bigger, then velocity would have to drop. In this case, however, they're asking, but the flow rate is increasing. Okay, so coming in from the left, we have increasing flow. So how do we get acceleration equal to 0 for any x at t equals 1 second, and explain how the acceleration can be 0 if the flow rate is increasing with time? And essentially this, what we expect is that there's going to be a trade-off then between the the flow rate change and this expanding sort of cross-sectional area. Okay, so let's start with something we know. We know that the acceleration vector, is equal to del v del t plus v dot the gradient of velocity. Okay, so what this means then is we have del v del t, so the change in velocity with time, plus, and then we have this component where we say this plus v dot del grad v is the velocity vector multiplied by the gradient of velocity, or the change in velocity in all three directions. Okay, so that's what our gradient operator does here. Now, ultimately, we're not going to care about anything but in the x direction. But for now, let's just start with, don't forget, we're going to start this with u is being equal to u of x comma t. We say v is equal to 0 and w is equal to 0. These are lowercase. So in other words, we only have an x component, we don't have a y component, and we don't have a z component of velocity. Okay, so this is going to simplify our equation to just work in one dimension. So what this then becomes, this acceleration vector is equal to del u del t plus u del x. So in other words, how is the one-dimensional velocity changing with position? All of this times the I hat vector, that's supposed to be an I. This will be equal to the acceleration in the x direction times the I hat vector, where u is equal to v naught, as we were given in the equation, or in the problem statement here, v naught times 1 minus e to the minus ct times 1 minus x over L, some length L. Okay? All right, so just check here. Yeah, okay. So we can write this now as a in the x direction is equal to 1 minus x over L times, and then I'm going to put in this bracket, c times e to the minus ct, right? So that's our derivative of u with respect to t, minus v naught over L times 1 minus e to the minus ct, and that quantity squared. Okay, so there's the sort of advance here to get through. Oh shoot, did I skip a step? What did I do here? Oh shoot, I did skip a step, my bad. Yeah, how did we get there so fast? All right, sorry about that. We'll get to this in just a second. My apologies, I jumped forward. Let's take the intermediate step, which is ax is equal to v naught times 1 minus x over L times c e to the minus ct plus v naught squared 1 minus times 1 minus e to the minus ct. Close that. We're going to square this times 1 minus x over L times minus 1 over L. Okay, sorry about that. So we expand this out, we take the derivatives where needed, and now we can write this, what we had on the previous slide, where I jumped a step. A in the x direction, the acceleration in the x direction is equal to 1 minus x over L, and then times this c to the e, times e to the minus ct, and then we subtract v naught over L and multiply that by 1 minus e to the minus ct. close that, we square this, and put a bracket on that. Okay, almost there, but not quite. Okay, so that's our general expression, but then we were given these conditions. We said for or if AX is equal to 0 for any X at this time t equals 1 second. Okay, so what that means then is that the right hand, this bracketed piece, has to be equal to 0. So in other words, the bracket of c e to the minus ct minus v naught over L times 1 minus e to the minus ct, and then that quantity squared. That whole thing has to be equal to 0, with v naught being equal to 10 and L being equal to 5. And those were also given in the problem statement. We said 10 feet per second and L being equal to 5 feet. Okay, so when we plug those in, we get c e to the minus c, c. Remember, we're looking for c. We're given a t, not a c. Minus 10 over 5 times 1 minus e to the minus c squared is equal to 0. And so we can solve for c being equal to 0.49, and the units end up being seconds to the minus 1. So I'm just going to put 1 over second. So we could have 0.49 per second or over seconds. So for the conditions of the local acceleration, so that's the c that we were looking for. So now the explanation is for the sort of above or given conditions, the local acceleration del u del t greater than 0 is precisely balanced by the convective deceleration, or the negative deceleration, negative acceleration, which is u del x being less than 0. So the flow rate increases with time, but the fluid flows into an area of lower velocity. Which matches our expectations that we talked about at the very beginning if we had kept Q constant. All right. Okay, last problem here. Looks like this. This is acceleration along a curve. Water flows over the crest of a dam with speed v, or velocity capital V, as shown in the figure. Determine the speed if the magnitude of the normal acceleration at point 1 is equal to the acceleration of gravity, g. Okay, so we're given a radius of curvature at that particular point of 2 feet. All right, so here's our radius that's defined for a centroid of this curvature that's at that point. And essentially, we note from the book that the normal acceleration for these circular systems is equal to v squared over this r radius. I don't have quite as nice a script r as the diagram here. So in this case now, we are given that this is equal to gravity g, and we're given this in feet. So I'm going to say this is equal to 32.2 feet per second squared, right? So that is what this has to equal. So what is velocity? So we can basically work this out that v is equal to the square root of a sub n, our normal acceleration, times this radius, and therefore we basically have 32.2 feet per second squared times a radius of 2 feet. And then we take the square root of that product. And when we do that, v comes out to be 8.02 feet per second. Okay, so that one happens to be fairly straightforward because a sub n is dictated to be equal to g, in this case, the gravitational acceleration. Okay, that was practice problem 4.44 from Wiley Plus from the end of the book, and I think that's all that I've got. So with that, I'll go ahead and end. Hope you guys find this somewhat useful. I realized there was a bunch of tedious calculus in the first two problems. That calculus ends up being somewhat important, but for the most part, I think if you've worked through some of the problems already in Wiley, you'll have seen some of that already. So with that, I hope you guys have a great day, and I'll look forward to seeing you in class.